So when I speak about the country's space exploration program, it is going to remain incomplete if I don't speak about Professor Sisir Kumar Mitra, and he is known for his enormous contributions in the domain of ionospheric physics. And he was the first person in India to have used the radio waves to sound the ionosphere of the Earth. And that you can consider as the first experiment wherein radio waves were used for remote sensing of the ionosphere. So he has written a legendary book, The Upper Atmosphere. So today, when we speak about the Sun-Earth connection or the space weather, many scientific concepts, it is him who has implanted in this branch of physics. We have to remember that the India space program had a very humble beginning, but very sincere beginning. His time was around 20s and 30s, but soon after that, when India was moving towards on the verge of getting independence from the British Raj, India was having its own problems of political instability. And it was that time when two illustrious sons of Mother India stood as pillars of determination. One was Dr. Homi Bhabha. He said that we have to build up outstanding schools of research if you have to do excel in scientific research. And Dr. Vikram Sarabhai, whom we consider as the founder of the Indian space program, father of the Indian space program, he said we must be second to none in the application of advanced technologies to the real problems of man and society. One thing you have to remember, unlike the other space agencies today, Indian Space Agency, ISRO, or the Indian space program per se, it started from science and societal applications, not as an offshoot of defense. So you have to remember this difference very carefully, and that is the reason behind the success of ISRO. And speaking about 1940s, the pre-independence era, Dr. Bhabha founded the Tata Institute of Fundamental Research, TIFR, in 1945, and Vikram Sarabhai founded the Physical Research Laboratory in the city of Ahmedabad in 1947. And these two institutions, TIFR and PRL, played enormous role in setting the initial conditions of the space exploration of this country. In the year 1947, on the 15th day of August, India was independent. And although India was independent, it was having its own problem of feeding people, poverty. It was having its own problem of instability. And during that time, when India was a newborn independent nation, then pillars of Mother India, Dr. Homi Bhabha and Dr. Vikram Sarabhai, they contributed tremendously to build the scientific infrastructure of the country for the space exploration. So what you can see in this picture is the picture of Dr. Homi Bhabha with some balloon-borne experiments which he was doing from the Tata Institute of Fundamental Research, Hyderabad. And during the time of 1940s to 1950s, he and his team conducted lots of experiments using balloons as platforms in the realm of cosmic ray physics. And the balloons were attaining an altitude of 30 to 40 kilometers. And this facility exists till today. If you ever visit the city of Hyderabad, you will be able to see the National Balloon Facility, NBF, where they still fly balloons, high altitude balloons, which soar to the altitude of 40 kilometers with scientific instruments. And while this happened in the era of 1960s, something else happened, and that was significant for the foundation of the formal space exploration of the country. So what happened? The Thumba Equatorial Rocket Launching Station, TULS, that was established at a very sleepy village near the city of Thiruvananthapuram in the state of Kerala, in the southern part of India, in the banks of the Arabian Sea. And the sky of Thumba is the one where the ionospheric ring current passes. And that is the specialty which made the land of Thumba very special, because if you have to study the ionosphere on the geomagnetic equator, and if you still should have a sea coast in order to launch some rockets, that was the place post the ideal scenario. And Professor Vikram Sarabhai chose the Thumba, the fisherman's village, for this purpose. And what you can see in this picture, the left hand side of the left hand side panel, the Equatorial electrojet, which is shown as an enhancement of the magnetic field, geomagnetic field, and this was the scientific attraction for the upper atmospheric physicists and the ionospheric physicists that time. And people were trying to get the means to access the upper atmosphere and ionosphere, and hence TERLs played a very significant role in setting up the space program. So in 1960s, you have to remember, during that time, ISRO per se was not born yet. So during that time, Dr. Vikram Sarabhai convinced the government, the then government, of the value of a space program and emphasizing its role in applying technology for societal benefits in a developing nation. And what happened at the time, we didn't have our own rockets. So the first rocket launching station was established in Thumba, and the first launch, the inaugural launch, happened with a scientific payload in 1963. All of you know, with the Nike Apache rocket. So 1963 marked the beginning of the sounding rocket exploration from the lands of Thumba. And if you see the early days of the space program, 1962, the Indian National Committee for Space Research, INCOSPAR, was founded under the Department of Atomic Energy. And 1969, 7 years after the constitution of INCOSPAR, the Indian Space Research Organization, ISRO, was established in August 1969. To be more precise, it was 15th August 1969 in place of INCOSPAR. And June 1972, the Space Commission and the Department of Space were constituted, and ISRO was bought under the Department of Space in the September 1972. So it started its journey sometime in 1969, but it took 3 years to constitute the Department of Space, and then ISRO was brought under the Department of Space. What you can see in this picture is the church, St. Mary Magdalene Church, which is situated in Thumba. This church was dedicated by the bishop and the local fishermen for scientific experiments. And in this building, the initial scientific experiments is to take place, and the Thumba was used as the rocket launching station. And you can see this iconic picture. Many of you might have seen this picture. A nose cone of a rocket is being carried on a bicycle. So in 1968, on 2nd day of February, the Thumba Equatorial Rocket Launching Station, TERLS, was dedicated to the United Nations by the then Prime Minister Indira Gandhi. And this became a landmark in the history of the Indian space program. You have to remember, when you dedicate this facility to the United Nations, it becomes accessible to the scientists internationally. So when you make something available internationally, not only you're doing something with a greater good cause, at the same time, you're attracting resources in terms of technology, in terms of wisdom, in terms of resource, facility, everything to be set up in a then developing country. I'm speaking about the year 1968. So whatever TERLS is today, it would not have been had these kind of decisions not been taken. So by the time ISRO was born, I have mentioned 1970 and 1969 ISRO was born. 1975 to 1976, these years witnessed a very strong international cooperation, international collaboration. Dr. Sarabhai's dialogue with NASA led to the satellite instructional television experiment site. Many of you remember, those who have seen those days in 1970s. Maybe I was not born during that time, but the seniors who have seen those days, you will definitely remember 1970s was the time when the black and white TV was introduced, and that was not very common. And during those days, only one television used to be in place, and people used to come assemble to and watch the program. So that was the case in satellite instructional television experiment. So the nation was a newborn independent nation, and there was a need to educate the people, impart a lot of knowledge education to the people, and that's how the space was used to educate people in terms of the TV program. And in terms of scientific activity, also another very important thing happened, that there was a satellite of NASA called ATS, Advanced Technology Satellite, ATS-6. This satellite was used for, the beacon from this satellite was used for ionospheric studies. And this is the lead institution, or the lead laboratory for this was the Space Physics Division of the Vikram Sarabhai Space Center, Trivandrum. So in those days, the Space Physics Division was the one that used to take significant role in ionospheric or upper atmospheric experiments. Space Physics Division later got transformed to Space Physics Laboratory, and it is still there in the Vikram Sarabhai Space Center as Space Physics Laboratory, carrying the legacy of the olden days. Now, in 1960, between 1960s to 1980s, lots of other things went on happening. So what happened during this period? TIFR and PRL joined hands to develop instruments for hard X-ray studies from astronomical sources with the balloon as a platform. And these experiments used to be flown from the TIFR balloon facility in Hyderabad. And PRL and TIFR, again, PRL has taken the lead for X-ray experiments, again, on board the rockets. And 1 to 10 keV sources used to be studied. And these rockets used to be flown from Thumba and Sriharikota. You know about Sriharikota, where from all our big satellite launch vehicles are launched nowadays. So parallelly happened. You have to see, on one hand, from Hyderabad, the balloons used to be launched with X-ray instruments, X-ray payloads. And from the lands of Thumba and Sriharikota, X-ray instruments used to be launched on both rockets. And the rockets also used to carry the ionosphere and upper atmosphere studying instruments. And courtesy, again, the Space Physics Division, which is now the Space Physics Lab in the Vikram Sarabhai Space Center. And PRL also took some lead during this time to study the solar activity influence on the cosmic rays. So how many domains were taking birth in terms of scientific exploration, space-based scientific exploration in a newborn independent country? It was X-ray astronomy, which was taking birth. It was the ionospheric physics, upper atmospheric physics, solar physics, and cosmic ray physics. And people were making scientific instruments for this purpose. And this had a very, unique repercussion. It was a training ground for the scientists to build scientific instruments or payloads for the satellites. You know, when you build some instrument which is supposed to work in satellites, it is not an easy job. Space has got its own problem. It has got vacuum, deep vacuum. It has got problems of high energy particles. It has got problems of thermal engineering. It has got problems of telemetry, how to get the data, how to command. So there are certain set of problems which are specific to instruments which are flying in satellites. And these balloon experiments and the rocket experiments were the breeding grounds for the future satellite experiments, and the scientists were getting ready to lots of failures and successes. And this culminated to the development of the indigenous satellite from our country, the Aryabhata. And this satellite was flown in the year of 1975 from a Soviet launch facility. And the instruments which this satellite carried included X-ray astronomy, aeronomy, and solar physics instruments. So aeronomy is a term which is used to tell about the physics and chemistry of the upper atmosphere. So it is not astronomy. So many of you may already know, but assuming that many of you may not be familiar with the term aeronomy, I am explaining. So in the picture, what you can see is the completely designed and fabricated in India and launched by a Soviet rocket on April 19, 1975. Soon after that, in 1981, Bhaskara II was launched, and Bhaskara II also was launched using a Soviet rocket. And you have to remember that it was the Earth observation satellite. So today, when we speak about space science exploration, we usually do not tell about the Earth observation, because Earth observation we have differentiated as some other application. But we have to remember this Earth observation satellite also played a very important role when we speak about today remote sensing of the other planetary bodies like Moon and the Mars. In the future, we might do something else. So these were the beginnings. And meanwhile, something else was happening. You have to remember that we started with sounding rockets. So by the time sounding rockets have flown and it carried several payloads of X-ray, upper atmosphere, ionosphere, but need was felt that we are making our own satellites. But those satellites have to be launched from the other country. Why don't we make our own launch vehicles? And the launch vehicle domain was a newborn domain in the space exploration in the country, which was one step ahead of the sounding rockets. And many of you are aware that our beloved APJ Abdul Kalam sir was working in the development of the SLV-3 rocket. So let us speak about the SLV-3 rocket. SLV-3 rocket launched a series of satellites, Rohini series of satellites between 1979 to 1983. And the first one was Rohini technology payload RTP, but it could not be placed into the orbit. But then Rohini RS-1, RS-D1, RS-D2, they flew on board the SLV rockets, and their objective was not that much scientific, but it was more of a health checkup. Like RS-1, the camera was for studying the fourth stage of SLV. D1, it was having a solid-state camera for remote sensing applications. But when it came to D2, the camera was for visible and IR mapping. So you have to see very silently the transformation which was happening. Camera, we understand, we take all images in the visible wavelength. But now we are going it's some part of the electromagnetic spectrum where it is not visible with bare eyes. We are going to IR imaging. So this is the time when we are slowly started exploring other parts of the electromagnetic spectrum for imaging. And some of you may ask, what is the meaning of D1, D2? D means development flights. So now between 1987 to 1994, there was a series of satellites which we called the Stretched Rohini Satellite Series, or SROS. The previous ones were Rohini. So these are Stretched Rohini. And the payloads were gamma ray astronomy, upper atmospheric studies, and the launch vehicle also had a transformation. The Rohini series were flown in SLV-3. These stretched Rohini series of satellites were flown on board ASLV, which stands for the Augmented Satellite Launch Vehicle, and the capability was 150 kg to low Earth orbit. The previous one, SLV-3, was capable of launching 40 kg. So this is almost 4 times in terms of the payload capacity. And what were the augmentations? A very much visible augmentation was the strap-on technology, which you can see here. The subsidiary rockets on the either side, these are called strap-ons. Strap-on technologies were new. In order to get a very good lift-off capability, you should have those. Inertial navigation is another one. Inertial navigation means, inertial term, many of you are familiar. Inertial means which is sensitive to force, sensitive to acceleration, right? Force is nothing but mass into acceleration. If a system is sensitive to force or sensitive to acceleration, it is called an inertial system. So if you have an inertial system, if you integrate once over the time, you get velocity. Is it not? If you integrate a force or say acceleration per se, acceleration, if you integrate with time, you get velocity. Velocity, once you integrate over time, you get position. And once you know the initial position, you know where you were. So inertial systems are very important for rockets as well as for the satellites. And ASLV had the first inertial navigation system for the rockets. This is important. Why am I telling? You will be able to understand from the next slide. So As I told you, the gamma ray bursts were studied in the previous stretch Rohini series of satellites. The gamma ray bursts, those who are familiar with the domain of astronomy will appreciate. Gamma ray bursts can happen anywhere in the sky. Not necessarily you have a fixed target. So the instruments which you have to carry should have a very large field of view, and you should be ready to accept your signals from any part of the sky. So it is a wide field of view instrument which you have to send to the sky. But when we got matured in the realm of X-ray astronomy to study the X-ray binaries, the fields which we have chosen, which needed pointing towards a given source. And when it was required to point towards a given source, it needed the technology of inertial pointing, and also it needed more mass and power, because not only you should have an inertial system, you should have your kinds of subsidiary systems like reaction wheels, momentum wheels to look at a particular direction, and this will consume some mass and power, and some developments took place. Inertial systems for attitude control of the satellite started being developed. And so that was the time, 1990s, when these inertial systems were getting developed indigenously in the country. Star sensors were developed as reference. By seeing the pattern of some stars, you know where you're pointing. And associated control system, because you have to achieve a given degree of accuracy in the pointing. So when these things happened, there were another thing which was happening in the realm of launch vehicles. So ASLV was not sufficient. It came as PSLV, the Polar Satellite Launch Vehicle, with an enhanced capacity of 1750 kg to the sun synchronous orbit, which is the altitude is around 600 kilometers. So in 1996, the Indian X-ray Astronomy Experiment, IXAE, was flown on board IRS-P3. And you have to remember that this experiment was not the only experiment flying IRS-P3. There were other experiments as well, but they were Earth observation kind of experiments. But when I'm speaking about scientific exploration, I want to emphasize this IXAE experiment was one of the instruments in the IRS-P3. And you have to note this: the field of view which was achieved was 2 degrees to 2 degrees, and the energy range of the source which was at rest, it was 2 to 20 kilo electron volts. And there were several observational studies of bright X-ray binary star systems, including X-ray pulsars and stellar mass black hole candidates. And there were studies of mass accretion around neutron star and black hole binaries. Those were some of the major outcomes, and which I have not mentioned here, it has given rise to many PhDs in the field of X-ray astronomy. Now, if you remember that time in the late 1990s, when we were doing all these things, what was happening globally in the world during that time? The Hubble Space Telescope of NASA was already operational, and the Compton Gamma Ray Observatory CGRO of NASA was also operational, and getting ready were the Chandra X-ray mission and XMM Newton. All these were very good astronomy missions. Now we have started very humbly with our astronomy mission. Now we have to play some meaningful role globally, right? We should find some domain where nobody else is doing. We have to add some value accordingly. So what should we have done? Should we have gone for a better resolution, or should we have gone for a better sensitivity? So technology was a big barrier during that time. If you remember, I'm speaking about late 1990s. Then, out of a lot of brainstorming, the decision which was taken, let's make the USP as multi-wavelength astronomy. So, as you're aware, those who are doing any kind of science using the electromagnetic spectrum, every part of the electromagnetic spectrum has got some story to say. When you're observing something, short wavelength, long wavelength, medium wavelength, everything will have something to say about some process which is happening. So if you have a multi-wavelength observation, it provides you an opportunity to study lots of physical processes which will allow you to understand the physics of a star or as astronomical source, it is wholesome. So it was decided that the near and far ultraviolet and soft and hard X-ray bands will be covered in an astronomy observatory from India. And that was the beginning of birth of AstroSat in 2015, which still continues. And this was the India's first multi-wavelength observatory, and which had some instruments like ultraviolet imaging telescope, soft X-ray telescope, large area X-ray proportional counter, cadmium zinc telluride imager, scanning sky monitor. So this observatory, India's dedicated astronomy observatory, multi-wavelength astronomy observatory, has been credited with lots of discovery class of findings. So you must be feeling proud to recall that a few discoveries which it has made include witnessing the light formation of dwarf galaxies using the ultraviolet part of the electromagnetic spectrum, detection of UV light emission from a galaxy at 9.3 billion light years away from the Earth, solving a decade-old puzzle of a source which is both hot and cold. So there are so many. So if you can see the publications, you'll be able to see the kinds of PhDs it has yielded and the kind of scientific discoveries AstroSat has done. So if you recall this metamorphosis of the space program, 1960s to 1970s, we call it a initiation phase of the space program. 1980s was the experimental phase, 1990s was the operational phase, 2000 was the expansion phase where we have started speaking about space science missions. You have to remember that so far before 2000, the kind of scientific experiments which we used to fly, they were mostly, not dedicated science missions. They were scientific instruments which were piggyback or co-passengers with some other experiments. But dedicated space science missions started in 2000 onwards. And 2020 onwards, I call it an inclusion phase of ISRO because of the space sector reforms and the policy, space policy was rolled out in the year 2023. And it was the time when ISRO has become very much inclusive to synergize the might of the other stakeholders in the realm of the space exploration. So today when I'm speaking with you, the major space exploration verticals include the exploration of the solar system, astronomy, astrophysics, solar and heliophysics, and near Earth space. And over above this, as you're aware, today there is a human spaceflight program, which will also add some extra dimension to this program because when this program becomes stabilized, we will also have some scientific experiments which can be done by astronauts from the space. We call them astronaut in loop experiments. So this is the journey and the roadmap. I need not dwell on this. Whatever I have told, recollected, all are captured in this roadmap. And very recently, we have flown in 2023, Chandrayaan 3 and Aditya L1 and the EXPOSAT satellites, something I will mention. Meanwhile, when I was speaking about what has happened 2000 onwards, on the 15th day of August 2003, Honorable Prime Minister of India announced the Chandrayaan 1 mission. And in 2004, during the month of November in Udaipur, India, there was an international conference on exploration and utilization of the moon. And in this meeting, Honorable President of India, now other than Dr. APJ Abdul Kalam sir, mooted the idea that it is important that India sends something to reach the moon's surface, not merely an orbiter to rotate, to revolve around the moon. And that's how the idea of the Moon Impact Probe MIP was mooted. And on the 14th day of November 2008, many of you know that the Moon Impact Probe was released from Chandrayaan 1 orbiter and which was made to impact at the 89.5 degrees south and 122.9 degrees west. And this was the first man-made or human-made object to have impacted from Asia continent on the moon surface. That was from India. And this impactor was not a mere impactor. It was carrying scientific instruments called CHASE, Chandra's Altitudinal Composition Explorer, which studied the lunar exospheric noble gases like argon, neon, helium, also the molecule of hydrogen. And this CHASE instrument was the first instrument to have detected the lunar exospheric water in its vapor form. And I take pride personally when I speak that I have worked in 2008 in this moon impact probe endeavor, and I have worked in the with the instrument CHASE, and my PhD work was in the science of CHASE. So if you see the India's lunar exploration program, we had so far sent 3 missions: Chandrayaan 1 in the year 2008, Chandrayaan 2 in 2019, and the Chandrayaan 3 mission, the recent one, in 2023. Chandrayaan 1 was an elegant example of an international cooperation. It comprised several scientific instruments, some of which were purely from Indian origin, some of which came from the European countries, some of which were European-Indian cooperation, and some of them came from the United States of America. And the broad objective of Chandrayaan 1 was chemical, mineralogical, and geological mapping of the moon. And this same theme continued in Chandrayaan 2 with similar set of scientific instruments, while after having understood the moon globally. So when I say globally, I mean when you have a satellite around the moon, you are seeing the entire moon, right? So that's why I call globally. And you have understood a lot of things, which I will tell you in subsequent slides very briefly. You also wanted to send a lander and the rover in Chandrayaan 2, which due to technical reasons was not successful, but which was made successful in 2023. And we have achieved the soft landing on the moon near the South Pole with some of the scientific instruments. And the theme was ground truth of the surface and near surface properties at the landing site. So you have to see this wholesome. The orbital missions were chemical, mineralogical, geologic mapping of the moon entirety, and the lander mission was, and the roving mission was the ground truth of the surface and the near surface properties. So if I speak about the Chandrayaan 1, the scientific impacts, it has caused a paradigm shift in the lunar exploration, lunar science. I will say that several concepts about the moon which we had so far for decades have been transformed overnight. A few examples include, we used to think moon is bone dry. Chandrayaan 1 mission proved it is not so. It discovered the presence of water molecules on the surface of the moon. On the surface of the moon, it was detected as hydroxyl radical by virtue of the M-cube instrument, which was given by US. On the other hand, the CHASE instrument did a direct detection of the water as water molecule by in situ measurements of the exosphere. And this discovery caused a resurgence of the global interest in the lunar exploration. So when you speak today's lunar exploration, one of the important criteria is lunar hydration, the study about the water on the moon. There was a belief that moon is geologically dead billions of years ago, but Chandrayaan 1 has found evidences of recent volcanic activities. When I say recent, it is a few tens or hundreds of million years, which shows that the moon is still dynamic. There was a belief that moon's powdery surface, the regolith as we call it, they completely absorb the solar wind that come from the sun, which is very much rich in hydrogen and helium ions, and also the ions of some heavier elements. Chandrayaan 1 proved that it is not true that entirely 100% of the solar wind gets absorbed by the lunar regolith. It showed that around 20% of the solar wind protons get reflected back to space as energetic neutral hydrogen atoms, which you can see in this second picture in this cartoon. And then scientists also went one step further. using these energetic neutral atoms which were coming as a scattered or reflected component from the moon's surface, scientists have observed those energetic neutral atoms and backtrace them to understand the small patches of magnetic fields on the moon's surface. We all know that the moon does not have a magnetic field. The correct statement is moon does not have a dipole magnetic field like the Earth has. Okay, so that was our discovery, the discovery of patches of mini magnetospheres of the surface of the moon. And also there were other discoveries, observations, which show the hope of human settlement on the moon until and unless we come up with some technology of capsules, human capsules, which may be there on the moon. Chandrayaan 2 flew with some extended science objectives from Chandrayaan 1. There have been improvements in the scientific payloads, improvement in the observation strategy, and by this time we had the LVM-3 launch vehicle. Chandrayaan 1 flew in a particular configuration of the PSLV. This was launched with the LVM-3 launch vehicle Mark III. And the orbiter is still working and giving very good signs. Lander and the rover could not work, as I have mentioned, due to technical reasons. So what I am showing here you is the picture from the highest resolution camera anybody has ever flown in a satellite revolving around the moon. The orbital high resolution camera is the highest resolution camera which has been flown so far in any lunar mission, that is from India, and which has a resolution of around 25 centimeter from an altitude of 100 kilometer. So it is just like a foot scale. So from an altitude of 100 kilometers from the moon's surface, you are able to see a foot scale. And this helps you to see small features. So I don't have much of a time to tell what is the significance of this kind of a high resolution. Maybe later when I get the opportunity, I can discuss on this more. This tells about the lots of observations and very significant scientific results which have come out from Chandrayaan 2, from the domain of hydration, from the domain of surface physics, elemental composition, neutral and ionoxide exosphere of the moon, and also Chandrayaan 2 did, to a good extent, solar and heliophysics observations. So in some other occasion, if I get some time, I shall speak more about the scientific results. I don't have time because I have to cover a few more things, as my job is to give you a glimpse of the entire journey. So then came Chandrayaan 3. Chandrayaan 3 was launched using, again, LVM-3, and it was launched on the 14th day of July 2023 from Satish Dhawan Space Center, Sriharikota. And we went through multiple slingshots and then got stabilized in the moon's orbit, then multiple maneuvers, and then finally we landed on the moon, soft landed. The scientific instruments which we have carried in Chandrayaan 3 included a few instruments on the lander, a few instruments in the rover, and you have to remember that apart from the lander and the rover, there was a third component in the Chandrayaan 3 mission. The third component was a propulsion module which has carried the lander rover system from the Earth to the Sun. The lander was housing an instrument called ILSA for studying the ground vibration of the moon's surface due to seismicity or some other reasons. JASTE, which is a thermophysical probe, which was inserted into the regolith of the moon to study the thermophysical properties up to a depth of around 10 centimeters. Rambha Langmuir probe for studying the lunar near-surface plasma environment. And also there is one passive instrument which was given by NASA, a lunar retroreflector array, wherein it is to happen like this. The Lunar Reconnaissance Orbiter of NASA had a laser. So this, with the laser, they used to fire photons onto this LRA, on this lunar retroreflector array, and they used to get the reflected laser to understand the distance between the LRO and the landing site of the Chandrayaan 3. which helps to understand a lot of other physics, which may be beyond the scope of this discussion. The rover, on the other hand, carried instruments like alpha particle X-ray spectrometer APXS and laser-induced breakdown spectroscope LIBS. Both were for studying the elemental composition and abundance in the vicinity of the landing site. And the propulsion module was carrying an instrument called SHAPE, which is a spectropolarimetry instrument, which was studying the Earth from the lunar orbit. In future, when we have exoplanet missions, we will be posed with a similar scenario. So as a precursor, we carried this instrument to see the Earth as a planet which is habitable with water and cloud. How does the spectropolarimetry signature look like? Similar experiences will be handy when we will have future missions in the search of habitable exoplanets. So the choice of the landing site of Chandrayaan 3 was also done with a lot of considerations. The scientific considerations included that the high latitudes were relatively unexplored. If you see this picture, it shows you the landing sites of the other space agencies' landers. Chang'e 4 is not shown. It has landed in the far side of the moon. So what you see here, nobody has gone to the high latitudes, which is scientifically important. And this poses a unique condition where the sun shines at the grazing angle, which means that the lesser deposition of energy and the solar wind ions and electrons are less numbered. And very scientifically interesting topography are available in the polar regions. And the technological reasons included, there are certain criteria of the landing, which include conditions on the global slope, conditions on the sizes of the boulders and craters. You should not land on some crater or the boulder and jeopardize the mission. Shadow analysis, because you will have solar panels. You cannot afford to have a shadow cast on the solar panels, which can stop the generation of power, electrical power. And yet another important facet was the communication with the Earth. So both technology and science dictated where to land, and this landing location of Chandrayaan 3 was named as Stasio Shiv Shakti. So Stasio Shiv Shakti is the name of the location where Chandrayaan 3 landed. So Chandrayaan 3, let me give you an update about the mission. So the soft landing was achieved and the demonstration of the rover movement was also done. Rover has moved around 101 meter on the moon surface, which you can see here. And this has become an iconic picture where the lander, which is called Vikram. Vikram is the name of the lander, and Pragyan was the name of the rover. Pragyan has taken a picture of Vikram, and this has become an iconic picture, the pride of the country. And also, there have been two more extended operations of the mission, demonstration of the hopping of the lander by refiring the engine when we were done with the scientific instruments, and when the sun was about to set in the moon sky, then we understood that we are done with all the experiments which we're supposed to do in the one lunar day. After wrapping up the scientific instruments and before we have put the lander to sleep, we wanted to demonstrate hopping of the lander by restarting the engine on the 3rd day of September 2023, and also the return of the propulsion module to the Earth's orbit. And both these were very humble beginnings, humble steps towards a future sample return mission. We all appreciate for the sample return mission to happen, a lot of other things are needed. But these two can be considered as a very humble beginning towards that bigger goal. In 2013, we have launched the Mars Orbiter mission, and which reached the Mars in the year 2014, and which was in orbit till 2022. And the journey was with PSLV launch vehicle. And telling about the journey, it is very crucial because every time you don't get the opportunity to have a mission to Mars, you have some launch windows, and The launch windows are very stringent. If you miss one launch window, the next window will come after a few months. Few months means around 19 months. Then that same opportunity may not be very much economical in terms of fuel. And this journey was very critical in the sense you have to have the correct amount of velocity at the correct location at the correct time so as to ensure that the orbiter will be captured by the moon's gravity, sorry, Mars gravity. If it does not happen, it will either get lost in space or it will be impacted on the Mars. So you don't want either. You want it to get stabilized in a Martian orbit. So we compared this with an analogy. If you have a golf ball in India and if you have a small hole in America, and it is like you are with this much accuracy, you are launching this golf ball from India and it is landing at that hole in America. So you are launching and there is a small cube with a few tens of kilometers dimension, a hypothetical cube near Mars. You are launching from Sriharikota. Your spacecraft has to be there within that cube with a particular range of velocity at a given time. Then only it will be captured successfully as an orbiter by the Mars. So before even that, there were challenges when we were having the mission, having the launch vehicle phase of the mission. There was no ground station to track the launch vehicle itself. And this was the time when we have made use of the shipborne launch vehicle, shipborne ground stations, and which was very challenging. You're tracking something from a hard ground and you're tracking something with an antenna on ship. The kind of stabilization systems you should have, the kind of other control systems you should have, that is a different domain by itself. And we must also acknowledge the different ground stations support by the other countries rendered for the success of this mission for the tracking, apart from our own 32-meter Indian deep space network and the other ground stations of our own ISRO telemetry tracking and commanding network, plus these shipborne terminals. And also, there were several other challenges. The challenges once you have placed the satellite into the orbit, there were challenges which are, due to the astronomical conjunctions between the Sun, Earth, and the Mars. Sun in the middle, Earth in one side, Mars in the other side, all in the straight line. We call it a blackout geometry. Or Sun in one side, Earth in the middle, Mars in the other side, we call a whiteout geometry. All these conjunctions are not very good when you are doing a communication with an electromagnetic wave. And these kinds of blackout or whiteout conditions remained not for hours, it was remaining for 14 to 17 days. And just imagine, for this 14 to 17 days, you are not able to communicate with the spacecraft, and there are certain operations which are needed to be done on the spacecraft. How to do it? Then you had to go for autonomy of the spacecraft, complete autonomy. You are not able to send any command from the ground station. You are not going to get any feedback what is happening in the orbiter. So autonomy was the need of the hour. There were other challenges as well, challenges in terms of the propulsion system, communication system, power system. You have to just think that you have done with the earthbound orbits, and now you have got the escape velocity and in the coasting phase towards the Mars. It took around 300 days in the coasting phase to reach, and for these 300 days, you have not used your propulsion system, and it is cold, deep cold in that space environment. Lots of ground tests were done that gave us confidence, and it was really heart trembling moment when we were about to switch on the propulsion system, when we were about to reach the Mars after a gap of 300 days. Communication system was yet another channel, because as you are going far and far from the Earth, signal is getting feeble. And when you are very close, signal is very strong. So you are going to deal with a very big range of the signal strength, starting from a very strong signal to very weak signal. And we had antennas of different gain stages. And same with the same challenges with the power system. If I have to go on speaking about the challenges which we have faced in this entire mission, it can itself be a lecture, a very thrilling experience indeed. And then we were ready to have the, getting into the Martian orbit. We were approaching the Mars, and we had to, as I mentioned, we should have the right velocity. We were coming with excess velocity, and we had to kill some amount of velocity. We call the operation as a delta V operation. So we had to reorient the spacecraft and fire a rocket in order to kill some velocity. That happened, and then there was a communication blackout, which was known earlier. And the radio link between the Mars orbiter mission and the ground station got blocked by Mars because the Mars orbiter mission was behind the Mars. And then those of us who were in the control center, and I was very lucky to have been in the control center. I was a part of the Mars mission. It was a pin drop silence at the control center. And then there was a time when communication was re-established. And you have to remember, when it came out of the Mars behind, immediately the communication was not established because there was a radio delay, which was, if I remember correctly, was in the order of 12 to 15 minutes something. So it came out behind Mars, and then the electromagnetic wave took that much time to reach Earth, and then there was applause that yes, we have inserted the Mars orbiter mission around Mars for the first time in the first attempt. So if you see the Mars orbiter mission overall, the first Mars mission in the world to have succeeded in the first attempt. The project was realized in the shortest time of 18 months. Most economical interplanetary mission in the world, the budget was mere 450 crores. The other contemporary missions, if you have to compare, it was around 6,000 crores. First Indian satellite having the full-scale onboard autonomy, the youngest team which has worked for this mission. Now, since I am having very limited time, I may not dwell on the intricacies of the science which we have got from the Mars mission. I will simply run through. Just to mention, we have got very good scientific questions, outstanding questions about the Martian exosphere, like what are the dominant gas constituents, how does the gas composition change with altitude, does it depend on the local time, or what is the exospheric temperature? With all these questions, we went to the Mars, and they were revealing scientific results from the MENCA instrument, the Mars Exospheric Neutral Composition Analyzer. And I was fortunate to have worked for this MENCA instrument. It is a mass spectrometer, like the way I worked in CHASE. MENCA is an advanced form of CHASE, and which has studied the composition and different other facets of the Martian exosphere. And there was coordinated observation, which another NASA spacecraft called MAVEN, which went almost in the similar time scale as the Mars orbiter mission. So after having this, we also had some discovery class of finding, like the discovery of highly energetic argon atoms in the Martian exosphere. Also, there have been very important scientific observations about the Martian dust storm effects on the upper atmosphere. The dust absorbs sunlight, it heats up, radiates it, and warming and expansion of the thermosphere happens. And the cooling process of this thermosphere differs between the morning and the evening. And that's how this kind of asymmetry which you are seeing is happening in the day and evening. This is the left-hand side of the morning, and the right side is the evening side. This is a very important observation where you are showing how far in the altitude the dust can go and how the dust can affect the upper atmosphere of the Mars. And there have been a lot of fascinating results on the carbon dioxide cloud, also the detection of the hazes, atmospheric hazes, then also the 1.65 micrometer albedo, which is very much important to study the surface features, different processes, and studying the craters, volcanic plains, and geologic processes, dust, and also to study about the exposed bedrock or the ice deposits. And the Mars was zonified very clearly in terms of this albedo, which is a very important scientific result. And there were also very interesting cases of imaging of the natural satellites of the Mars, called Mars, Phobos and Deimos. And because of the highly elliptical orbit of the Mars orbiter mission, where it went up to the distance around 75,000 kilometers from the Mars, and Deimos was somewhere closer to the Mars. So this got the opportunity to study the far side of the Deimos for the first time, and this opened up the opportunity to study the apparent differences seen between the texture of the near side and the far side of the Deimos. That is a different story altogether. So later on, we had missions on Aditya L1, the mission to study the sun, the first space-based dedicated solar observatory from India, which is placed in the halo orbit around the first Sun-Earth Lagrange point, which is about 1.5 million kilometers from the Earth, and which gives us a major advantage of continuously viewing the sun without any occultation and eclipses. And also, this would provide crucial information in understanding the impact of the solar activities on the near-Earth space weather. And there were several instruments. Some of them are remote sensing instruments, some of them are in situ instruments. So if I speak about Aditya L1 mission in a very brief way, it studies everything that comes from sun. So what all comes from sun? Sun gives us radiation, photons. Aditya L1 studies photons. It gives us solar wind. Aditya L1 studies the solar wind. With the solar wind particles associated is the interplanetary magnetic field. It studies the interplanetary magnetic field as well. So it studies everything that is coming from the sun, sitting at the strategically important L1 points. So we have to be very proud, because after NASA and ISRO, this is the third space agency to have a dedicated solar observatory at this important vantage points. The mission objectives are very scientifically critical to design and develop the observatory class of a satellite for uninterrupted measurements. The scientific objectives included to observe the dynamical events in the solar atmosphere, the photosphere, chromosphere, and the corona, spectroscopic diagnosis of the coronal plasma during the quiet time and the active phase. As you know, when I'm speaking with you, sun has become very active, and Aditya L1 is studying in situ measurements of the particle and magnetic field at L1 for heliospheric studies. And this is the kind of orbit where we have inserted this Aditya L1, which has happened on 6th January in this year. And this itself is a very critical operation. When I speak as a mission scientist, I know that how critical when you are placing a satellite around nothing. If you are placing a satellite around something, it becomes a two-body problem. A satellite around Earth, a satellite around the moon. But when you're speaking about a Lagrangian point, it is basically nothing. And on the two sides of the Lagrangian point, you are having two bodies. You are having sun, you are having Earth. Satellite is the third body. It is a three-body problem. And it is totally a non-Keplerian problem, which has got its own complexities, not only to achieve, but to maintain the orbit also. Then we had the EXPOSAT mission for studying the polarization of different X-ray sources in the sky, which made India the second nation after the US to have an X-ray polarimetry satellite dedicated in sky. And we had instruments with a big coverage, the POLIX, the main instrument, which studies the X-ray polarization in the range of 8 to 30 keV. And also we are having Expect payload, which studies the soft X-ray sources. POLIX is developed by the Raman Research Institute, and Expect is developed by URL Satellite Center, ISRO. And what we forgot to mention was, when I'm speaking about Aditya L1, many of the instruments have come from different other institutions other than ISRO. Like the Indian Institute of Astrophysics has given the instrument VELC, Variable Emission Line Coronagraph, and the IUCAA has given the instrument, the suit, the ultraviolet imaging telescope. So like the way it is not only ISRO, the institutions of India have also started building scientific instruments, and that is how we are growing now as a country. Now, before I conclude, I must tell you, you remember this website, issdistrict.gov.in. This website is an archival of all the space science data of ISRO. The recent mission data also will be uploaded. It is undergoing a process which we follow before we put this data in the archival. Presently, you will get some data up to the Chandrayaan 2 mission you're going to get in this website. And to summarize, Indian space research has a long legacy of ground-based and space-based observation. Today, apart from the space assets, we're having a very good strength in the ground-based facilities, ground-based observatories, ground-based radars, ground-based ionosondes to study the space in an integrated fashion. And the space-based observations started in the olden days with cosmic rays, X-rays, upper atmosphere, ionosphere, and then solar observation. And then when these observations, the scientific scope got increased, the launch vehicle capabilities also started expanding, and we started the planetary exploration in 2008. So far, we have sent missions to Moon and Mars, and observation platform capabilities also expanded. Not only an orbiter, we have achieved soft landing, roving, and also we have achieved placing a spacecraft in the halo orbit around the first Lagrangian point. And national level deliberations are also happening to define what is going to happen in future. So before I conclude, I'd like to draw your attention to a few books. These books are not meant for experts. It is for the space enthusiasts, which have been authored by me, but they're very humble books. This book is on the space exploration and introduction, which will give you an overall perspective of the space science and exploration. You can scan the QR code to get the book free of cost. Yet there is one more book which is on the solar system exploration and India's contribution. Again, not for experts. This will give you an overall perspective of the solar system, the exploration, and what India has done, what India has achieved in the domain of solar system exploration. This QR code gives you access to download this book. And the third book is the book on Moon, the Lunar Saga. This will give you an overall idea about the science of the Moon, the explorations of the Moon, and more details of the Indian lunar exploration. And this QR code will give you access to have this particular book. So let the journey begin. And let me tell you, there is yet another book. A new edition of this book will come maybe within a few months. This is a book which is a summary of the space science exploration and research which is happening in India. Those institutions who are doing some space science in some way, they are all their contributions or their work, which we have been doing for the last 2 years, they are all been compiled in this book. So maybe in a few months, a new edition of this book also will come up. That's all from my side, and thank you very much for your kind attention.